So if you have 3 steps, you have 3 activated complexes, and you will have 3 peaks on the potential energy diagram. The higher the peak from the original level, the higher the peak is from the original level of the energy of the reactants, the slower the step. Not how much does it go up from maybe the intermediates, but how high is it compared to the reactants? Okay, so you might have something that looks like this. And you might go, oh, well, that's not very tall, but it doesn't matter how tall that distance is. It matters how tall that distance is. Okay? Yeah. Did you guys catch that? Okay, good. So the activation energy for the overall reaction is the difference in potential energy. You go from the reactants to the highest peak. So the overall is the potential energy of the highest peak minus the potential energy of the reactants. And the slowest step will be the highest peak. Does that make sense? It's got the highest activation energy. Okay. And that is called, what do we call that step that is the slowest step? The rate determining step. Delta H does not change just because there's more than one step. Delta H is a state function, so it doesn't matter how you get from A to B, whether you do it in 1 step or 3 steps, delta H remains the same. So let's imagine that we have this little thing here, and we roll this ball up here. Sometimes people think, oh, the ball is going to get down here and it's going to get stuck. But it doesn't, because if you have enough potential, or if you have enough energy to get to the top of the hill, what happens as you go down a hill? You pick up what type of energy? Kinetic energy. So as it goes down, it's going to pick up kinetic energy. It goes up, it loses kinetic energy, but then it goes way down and it picks up a whole bunch more kinetic energy. And because it started with enough energy to get up to here, it'll be able to get to there. Okay, so it doesn't matter what the dips are in between, just whichever one is the highest peak. If you can get over the highest peak, you can get over all of the other peaks. Excuse me. All right. And if you recall, our activated complexes occur within the arrows, so we don't actually see them in the reaction. This is our reaction from last day. We had a slow step and then 2 fast steps, fast. And as you can see in our diagram, we've got, this is our potential energy here. Our first step is the highest peak because it is the slow step. And what is happening at the top of those peaks? You have your activated complexes. Three steps, 3 peaks. Yes?
Is it from like the dip to the activated complex, or is it from the original?
For that step, it would be, for step 2, it would be from here to here. Okay? But for the overall, it's always from the reactants to whichever peak is the highest, whether it's the first one, the third one, doesn't matter. Huh? Like highest overall. So if you go like this, all the others would be lower than it.
You don't have to bump this thing.
No, you just take whichever one is the tallest, and that is your activation energy of the overall reaction. So this would be the activation energy of step 2, because step 2 involves going from the intermediate to the second activated complex. But for the overall reaction, it's always from the reactants to the highest peak. And if you notice, the activated complexes are at the peaks. What's in the valleys? Reaction intermediates. Okay, so our reaction intermediates are in the troughs or the valleys. If you haven't heard of a trough, it's basically just something shaped like that, like a valley. Okay, usually the context you might hear troughs in is referring to like wavelengths, or a wave, the bottom is the trough. But you could also hear it as like a thing that a horse drinks from. A horse drinks from a water trough. Okay, and it's one of those things shaped like that, and there's water in it, and the horse drinks from it. That's it. Okay. All right, reaction intermediate. Could you please define reaction intermediate to your neighbor without looking at the book? All right, a reaction intermediate is a substance which is produced in one step and used up in a subsequent step. These steps do not have to be consecutive. It doesn't have to be 1 and 2. It could be 1 and 3, or it could be 2 and 4. Okay, as long as one comes first and the other comes second.
Like where's the activation energy is higher than one that was like.
You mean like this? Like the one I drew here?
Yeah, like
to say it doesn't matter?
Doesn't matter.
No, we talked about that. Because if it has enough kinetic energy to get over this peak, because it will pick up extra kinetic energy going down the hill, it will have enough to get over that peak.
Even if like the gap peak from the water to the top is shorter, it's longer than the one.
Yep. Doesn't matter. Just the one with the highest peak, always. All right. How to recognize a reaction intermediate. Hopefully you guys know that it appears first in the products and later in the reactants. That's going to be different from a catalyst, which we just saw last day at the very end of class. A catalyst, and you should be able to define a catalyst. A catalyst is a substance that speeds up a reaction. How does it do that? It provides an alternate pathway, and by pathway, we mean mechanism, with a lower activation energy. So there's 3 points in there. You need to say that it speeds up a reaction, it provides an alternate pathway, and it has a lower activation energy. And you should also state that it is not used up in the reaction. So that would be a good 2-mark question with 4 half marks. Yes? So what does that mean that it is not used up? What it means is that unlike a reaction intermediate, the catalyst appears first in the reactants, and then it comes out later in the products. So it gets reproduced. So did it get used up? Yes, question. Yes. It can just sit there and catalyze reaction after reaction after reaction after reaction. Do you guys remember hearing about the hole in the ozone layer? Yeah. It was an environmental disaster that happened like back when I was in high school. And do you guys know what the ozone layer does? It prevents the UV rays from basically scorching the entire planet and killing off all the life. Okay? So yeah. Okay, so when I was in high school, there was this big problem with it because there was a hole that was increasing in size year by year over both of the poles, but it was worst at the South Pole. And so you had to, all of a sudden, the sun was more powerful. There was a thinning in the ozone layer everywhere. And that was due to some chlorofluorocarbons, because chlorofluorocarbons are a catalyst for the breakdown of ozone. And so they would go up to the whatever layer of the atmosphere it was, the ozone layer of the atmosphere, and they would catalyze ozone breaking down into oxygen. And oxygen does not screen it does not screen UV in the same way. It does not absorb UV light the same way. So the UV light was then just coming through full force, and that was bad. So then they banned CFCs. They banned CFCs, chlorofluorocarbons. So they were carbon compounds that contained fluorine and chlorine, and they banned them. They used to be in air conditioning units, in refrigerants, and they used to be in hairspray. So they got rid of all of those. And then the ozone layer started to heal up again. Yeah, it slowly fixed itself because it's a big homeostasis system, it's homeostasis, equilibrium. Yeah. Okay, so here is a side-by-side comparison. You can see that the reaction intermediate appears first on the right in the products. It is produced, and then it appears on the left on the reactant side. Whereas the catalyst is the exact opposite. It appears first on the left, it gets used, then it gets produced. So a reaction intermediate gets used up as the reaction proceeds. A catalyst is not used up in the reaction because it comes back out somewhere before the end. And your job is going to be to identify the reaction intermediates and catalysts in the following reaction mechanism. So we have the uncatalyzed reaction. That's our overall reaction. Here's our mechanism. You might want to look at yours because I don't know that font shows up very well up there. Maybe it does. Maybe it's okay. So circle them, box them, put little clouds around them. Are we ready? Okay, who's got a reaction intermediate for me? Yes. Yes, here is a reaction intermediate. Are there any other reaction intermediates? Do you know? HCO, yes, we also have HCO. Any other reaction intermediates? Is hydrogen a reaction intermediate? It's a catalyst because it appears first in the reactants, then in the products. And what do you notice is left over after we go through, and if we were to cancel all those out, all we'd be left with is HCOOH. We would be left with CO, and we would be left with H2O, and that is our overall reaction, because how do you find the overall reaction? You add up the steps and cancel out anything that cancels out. Things that cancel out will either be reaction intermediates or catalysts. Beautiful. Oh, who is our rate determining step in this reaction? Step number 2. All right. So there we are. There's just a description there. All right. An aside. Okay, this is HCOOH. That is methanoic acid. Why is it called methanoic acid? What does meth stand for? 1 carbon. And when we have an oic acid, that means that you have a carboxylic acid. So ethanoic acid, propanoic acid, butanoic acid, those are all carboxylic acids. What does the structure of a carboxylic acid look like? Does anyone know? That is the COOH. That is a functional group, yes. Do you guys remember any other functional groups that we've dealt with? OH. OH is the alcohol functional group. Okay? Functional groups are just something other than carbon and hydrogen that gets slapped onto organic compounds. Okay? And in reality, it looks like this, where you have a C with a double bond O and a bond to an O and an H. And this R stands for the rest of the molecule. At least that's what I say it stands for. I don't think anyone else in the world says that, but that's what I say it stands for. So you should be able to recognize acids because either they begin with an H or they end in COOH, okay? And when they separate, it is important to know which of those hydrogens comes off, because hydrogen, an acid, the big deal about an acid is that hydrogen comes off, but we have lots of hydrogens, right? Which one is it? It's always the one attached to the COO. The other ones, not very much. Can you think why this hydrogen here would be more likely to lose its electrons and say, okay, oxygen, you take those electrons. Pardon me? And it becomes H plus, right? It comes off as H plus. And the oxygen, instead of having just here, it had 2 lone pairs. Now it has 1, 2, 6, 3 lone pairs. Yeah. It is because the difference in electronegativity. Oxygen has a high electronegativity. Do you guys remember what electronegativity is? How strongly they pull bonding electrons towards themselves. So, oxygen has a high electronegativity. Hydrogen has a medium electronegativity. I won't say low because metals have low electronegativity. Hydrogen is still a non-metal. Carbon and hydrogen have similar electronegativities. I'm just going to put En for electronegativity because that word is way too long. Hi, thank you. Question? So you can go whenever you doesn't matter. So does that make sense? Because oxygen is really good at pulling electrons, so it takes these electrons that are in the bond and it chucks them onto itself. Yes. Whereas carbon says, I will hold the electrons equally with you, hydrogen, and hydrogen's like, I will hold those electrons too, and so they just stay bonded. Okay? All right, since a catalyst is not used up in a reaction and it is always reproduced later, a very small amount of catalyst can catalyze a large amount of reactant. And that's why it was so important that they get rid of those chlorofluorocarbons altogether, that they have a complete worldwide ban on them. Because if you had some country somewhere being like, no, it's okay, we'll just do it, you would still end up with it being catalyzed, those reactions being catalyzed over time. And they would just go on and on. Potential energy diagram for catalyzed reactions. To find the activation energy of a particular step, like we said, you start at the beginning of that step and go to the peak. For the overall reaction, you go from the reactants to the peak. The following is a potential energy diagram of a catalyzed reaction mechanism. How many steps? 3. Which one is the rate determining step? 2. On the diagram, label the activation energy of the second step. Label the activation energy of the overall reaction, delta H the axes, and the activated complexes and the reaction intermediates. Off you go. So you can take a look and check your activation energies of the second step and overall. Remember, when you're drawing delta H, this end should touch where the reactants start, and this should touch where the products are. It shouldn't look like this, okay, because that's just too small. And it should point in the direction that the delta H goes. So in this case, it's going up. And then we have the axes. What is the x-axis? What can we label that? Reaction proceeds. What else? Time-ish. You could, we don't usually though, because that implies that it would have like some like linear amount, and we're not being very specific here. You know what I mean? Progress of reaction. And then there's one other weird one. Reaction coordinate. I know. I don't expect you to be able to come up with that, but if you see it, you should know that's what it's for, okay? Because it will show up from time to time. How about the y-axis? Potential energy. And what's the unit? Kilojoules per mole. Okay. And where do our activated complexes go? Tops the peaks. And where do our intermediates go? In the valleys. All right, excellent. There we go. Here is a potential energy diagram of a catalyzed versus an uncatalyzed reaction. I'm going to put a big star here. If you are given the catalyzed mechanism, which means you know the number of steps, then you should include the correct number of peaks. If you didn't know the catalyzed mechanism, you could just make the peak lower. Does that make sense? So if you don't know what the mechanism is, you're like, I don't know. Could be 7 peaks, 7 steps, could be 1 step, could be like 6 steps, who knows? You would just give it 1 peak. But if you happen to know that you have a 3-step reaction mechanism, then you should include the correct number of peaks. And if you know that the second step is the slow step, then you should make that peak the highest. Okay? The other ones don't matter, right? You just know that they're slower. They should just be lower. So it doesn't matter if peak 1 is greater than peak 3. Just kind of make a guess. Okay? All right. If you are not given the catalyzed mechanism, it is perfectly good, and you should just draw 1 peak to represent the catalyzed reaction. Okay, so that's 1.4c. There's some worksheet. Okay, we're going to finish the unit today, or close to it. So our next quiz will be on Tuesday. Wednesday, I don't care. Quiz Wednesday.
We all have a bio test on Tuesday.
Okay, that's fine. That's fine. Quiz Wednesday. And that's going to be on 1.3, 1.4, and 1.5.
Is it like similar to the quiz that we did?
Yep. And your test will be the following Monday. That is after the long weekend.
We have a long weekend?
You guys do? We have a Pro D Day on the 19th.
Oh.
Really?
Yeah. However, this class moves so fast that if you spend that entire weekend not doing any homework related to Unit 2, we will fall behind. So I expect you to be ready for your test on Thursday. Does that make sense to you?
Like next Thursday?
I would love to test you next Thursday. In fact, what I would really like is to test you next Friday, but there is no class next Friday. I would like to be kind and put the test on Monday.
That's too late.
But if you can't apportion your time and say, I am going to work on both Unit 2 and review Unit 1 on the long weekend, then we can't do it. Well, we can, it's just you'll be behind. Do you know what I mean? Like you'll be like way behind. So your quiz is on Wednesday. It should be on Tuesday, but we all have a bio test, right?
Yes, we do.
Okay. So you will get it back the Thursday before, so you can, go and study it. What's that? The test is going to be on Monday, the following Monday. Okay? All right, kinetic energy diagrams. Consider a beaker of water sitting on the counter. The individual water molecules in the beaker are in constant motion, but they are not all moving at the same speed. This is on page 105. So in fact, what I should do is I should give you guys the review material today so that you could do some of it this weekend. Can you drop by? I'll print it out at lunch and I'll put it on the chair outside my room and you can just drop by and pick it up before, at lunch or whatever. Yeah. Does that work? Okay. Or maybe I already have it. Hang on. Maybe I already have it. What? Now. I don't. Okay. That's all right. Consider a beaker of water sitting on the counter. Does this curve look familiar? This is a Maxwell-Boltzmann diagram. What unit did we use this in? The one that you're wishing that you had attended the lectures for. That was used in gases. Okay. Now, a large number of molecules, basically the area under the curve represents the number of particles. You may recognize the general shape as a basic bell curve. Hold on. However, this is a right-skewed bell curve. That means the right-hand tail is longer than the left-hand tail. For the purposes of Chemistry 12, we will refer to this as a kinetic energy diagram. If you're looking at AP, you're going to call it a Maxwell-Boltzmann diagram, okay? This graph illustrates that some particles have a low amount of kinetic energy, okay? Down here, we have a few molecules that are slow, have a low kinetic energy. Up at the top, in this middle pink section, we have a large number of molecules that have a medium kinetic energy. And there are also a few molecules that have a fast or high kinetic energy. And this curve, asymptote, it's an asymptote. Yes? So in theory, there could be a particle moving at infinite meters per second, or have infinite joules. In theory. So the total area represents the total number of molecules. The peak of the curve represents the most probable kinetic energy. So far, so good? Okay.
What is probable?
Likely. So which one are you going to come across the most often?
Oh.
Okay, so it's kind of like the mode. Most often. So how does this relate to reaction kinetics? Well, we have an activation energy here. And remember, an activation energy is an amount of energy on the bottom of this graph as we go from left to right. That is our kinetic energy. And remember, activation energy is a particular amount of energy. So let's say that the activation energy was equal to 10 kilojoules. 10 kilojoules will be on the x-axis, right? So we'll have 10 kilojoules here. And sometimes people get freaked out because when we had potential energy diagrams, the 10 kilojoules was on the y-axis and it was the difference between the reactants and the products. But now we're looking at the kinetic energy of the particles and that's on our y-axis. So what it means is that all of the molecules in this little green section down here, only the molecules with 10 kilojoules or higher are able to react. So in theory, if you did some fancy calculus, you could calculate the percentage of particles which have enough energy to react. Yes? Okay. Approximately what fraction, if you had to just guess, what fraction? What I might do is I might go, okay, I've got like a little triangle that looks like this, yes? And then I could say, oh, I got another triangle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, close enough. I'm going to say there's 12 things there. So that's going to be 1/12, which is 0.83%. About 1/12. You might guess 1/10. You don't have to be super accurate, right? And in fact, you're not actually going to be asked to read that off a graph at all. Okay, you're just going to be like, oh, look at that. What would happen if the activation energy were lower? Let's take a look at a different reaction with a different activation energy. That one has a lower activation energy. What fraction of that reaction? What fraction of particles will have enough to react? Probably 9/10 or something like that. What do you guys think? Close enough? 9/10 is close enough? Okay. So we went from having 1/12 in that one reaction because its activation energy was high. This reaction, the activation energy is low, so 9/10 of particles have sufficient energy to react. And that's as far as we're going to get today. Your homework is this, plus work on the review. Okay, and like I said, I will have that for you at lunch. Fraction?
What is the?
What do you mean? 9/10? 9/10 of this thing is green. So 9/10 of molecules have enough energy to react.
Oh,
Yeah?
that's what. So
Yeah.
isn't that basically probability?
Yeah.
Oh, okay.
Yep.
thank you. Do you want me to slide it back?
No, closed is good. Thank you.